8.5 Homogeneous and heterogeneous equilibria. 8.5.1 Homogeneous equilibrium. In a homogeneous equilibrium, all the reactants and products are in the same phase. For example, hydrogen in gaseous state plus iodine in gaseous state gives hydrogen iodide. The process is reversible. In the above equilibrium, hydrogen, iodine and hydrogen iodide are in the gaseous state. Similarly, for the following reaction, all the reactants and products are in homogeneous solution phase. CH3COO CH3 aqueous plus H2O in aqueous condition gives CH3COOH in aqueous condition plus CH3OH. CH3COOCH3. This is an aqueous condition. H2O, water, is an aqueous condition. CH3COOH, aqueous condition, plus CH3OH is also in aqueous condition. 8.5.2 Heterogeneous equilibrium. If the reactants and products of a reaction in equilibrium are in different phases, then it is called as heterogeneous equilibrium. Example, H2O in liquid gives H2O in gaseous state. The process is reversible. CaCO3 solid state gives CaO plus CO2. CaO is in solid state and CO2 is in gaseous state. 8.6 Law of mass action. In 1864, two Norwegian chemists, namely Maximilian Guldberg and Peter Wage, formulated the law of mass action based on the experimental studies of many reversible reactions. The law states that at any instant, the rate of a chemical reaction at a given temperature is directly proportional to the product of the active masses of the reactants at that instant. Rate is directly proportional reactant power x, where x is the stoichiometric coefficient of the reactant and the square bracket represents the active mass concentration of the reactants. Active mass is equal to N by V mole decimeter power minus 3 or mole L power minus 1. Where N is the number of moles and V is the volume of the container, decimeter cube or L, liters. 8.6.1 Equilibrium constants Kp and Kc. Let us consider a reversible reaction. Xa plus Yb gives Lc plus Mg. The process is reversible, where A and B are the reactants, C and D are the products, and X, Y, L and M are the stoichiometric coefficients of A, B, C and D respectively. Applying the law of mass action, the rate of the forward reaction Rf is directly proportional to A power x into B power y, or Rf is equal to Kf A power x into B power y. Similarly, the rate of the backward reaction Rb is directly proportional to C power L into D power M, or Rb is equal to Kb C power 1 C power L into D power M, where Kf and Kb are proportionality constants. At equilibrium, rate of forward reaction should be equal to rate of backward reaction Rb. Kf A power x into B power y should be equal to Kb C power L into D power M, or Kf by Kb is equal to C power L into D power M divided by A power x into B power y, which is equal to Kc, where Kc is the equilibrium constant in terms of concentration, active mass. At a given temperature, the ratio of the product of active masses of reaction products raised to the respective stoichiometric coefficients in the balanced chemical equation to that of the reactants is a constant known as equilibrium constant. Later, when we study chemical kinetics, we will learn that this is only approximately true. If the reactants and products of the above reaction are in gas phase, then the equilibrium constant can be written in terms of partial pressures as indicated below. Kp is equal to Pc power L into Pd power M divided by Pa power x into Pb power y, where Pa, Pb, Pc and Pd are the partial pressures of the gas A, B, C and D respectively. 8.6.2 Relation between Kp and Kc.